Hi, I'm Joseph Zhang, a developer of SELFE. I'd like to give you some tutorial on to show you how I set up SELFE and how to analyze the results. I hope it's useful. First of all, before we begin, I'd like to give you a very brief review of the model characteristics because some of them are relevant when we talk about how to set up the model. So SELFE stands for semi-implicit or inherent Lagrangian finite elements, and the name implies it uses continuous Galerkin finite element and finite volume approach. So it can use generic unstructured grids without any orthogonality constraints. So the time step in SELFE is done semi-implicitly, so there is no mode splitting between the internal and the external modes, as done in many other models. And the momentum advection inside SELFE is treated by using the so-called ordinary Lagrangian method, or EOM, and this is important characteristic of SELFE because it implies that the CF number in the model cannot be too small. So ideally, you want to make sure CF number is greater than 0.5 throughout the grid. If there's a small region where CF number falls below this number, it may be okay. And also, when you try to do convergence study with SELFE, many times you want to for the convenience, you just keep the grid fixed and vary the time step. But you need to be aware that when the time step falls below a certain threshold, the CF number will become very small and you may get strange results. So you can find this kind of information on the SELFE website. So something you need to be very careful when you apply the model. The vertical grid inside SELFE uses hybrid S and Z layers are optional. And the because of the finite element method we use, the volume conservation is not exact, but generally is very good. And we do have a mass conservative transpose using the upwind and higher order upwind as TVD. The model can be configured in multiple ways. For example, the Cartesian or spherical coordinates, 2D and 3D options, hydrostatic and non-hydrostatic models. And one thing I like to highlight here is that the bottom boundary layer formulation between the 2D and 3D SELFE models are very different. Okay, so this is something you need to be careful when you change from a 2D model to 3D model and vice versa. We do have higher order schemes for advection and momentum transport. And the so this method may become handy when you try to apply the model to your specific applications. The inundation scheme inside SELFE is well benchmarked, has been certified by National Tsunami Mitigation Program, and so we have done lots of benchmarks and validation studies using SELFE. So one thing I like to remind you is that if there's extensive wetting and drying inside your domain, CF number cannot be too large. Okay, generally speaking, without extensive wetting and drying, CF number can be as large as 10. But if you have extensive wetting and drying, you want to keep a CF number below, say, 2. And the model has been fully parallelized with domain decomposition MPI, and the scalability is generally good. And we try to follow good software engineering practice. So we set up the FSVN service for developers, and we do have 50+ automatic test cases to minimize bugs. So we do this fairly regularly whenever a new version comes out. So if you ask me to summarize the model characteristics in one sentence or in one word, that would be the fair. Okay, SELFE want to have all those desirable characteristics, meaning flexible, accurate, robust, and efficient. So this picture shows the SELFE modeling system as of today. So in the center you can see the hydrostatic and non-hydrostatic model and various components. And the model has been coupled to many other models and I'm not going to go through them in detail. So some of those models are in development stage, and others have been open released. As I said before, you can use non-orthogonal or triangular grids in SELFE. There's no orthogonality constraint. And this is the vertical transect of the grid. Looks like in SELFE. So you may place a series of Z layers below S layers, the Turing following layers. Okay, so the demarcation depth is called HS, and the transformation for the Turing following coordinates between the sigma and the Z is given here. It's the same as ROMs. Okay, so if you look at the S coordinates alone, you can have multiple ways to discretize the vertical column. So for example, the S coordinates are controlled by 3 parameters: HC, the minimum depth, and theta F and theta B. So when the theta F is very small, S coordinates becomes the traditional sigma coordinates. So you have uniform discretization along the vertical column. When the theta F is not small, then the discretization depends on the value of theta B. Theta B is varies between 0 and 1. When theta B equals 1, both surface and bottom boundary layers are resolved. When theta B equals 0, only the surface boundary layer is resolved. And when theta B is between 0 and 1, it's somewhere in between. So this may become useful when you try to tune the model to your own specific applications. So that's what how the model views the vertical transect. If you apply S and Z coordinates on top, this is Turing following coordinates. On the bottom, you have staircase profile resulting from the Z coordinates. Okay, let's look at the grid generation aspect of the model. So we typically use SMS, but you can use other softwares. Some of the concepts here are generic. So what you see here is the San Francisco Bay and Delta grid. So let's zoom in the upper stretch of the San Joaquin River, and already preloaded the DM grid. You can see the contour here. The positive number means that it's initially above the it's dry ground. So you can see that some stretch of the river has a very narrow channel, less than 10 meters here. Okay, if you define the channel line as 0.7 meters above the reference datum, so we need to modify the map here. So what I have done here is that I let the arch follow the 0.7 meter iso line on both sides. Okay, so you can see that the channel here becomes very narrow, but that's okay because that's the price to pay. Because otherwise the water will be blocked in this stretch of the river. So another thing you want to consider is that because the channel is so sinuous in this some part of the river, you may not be able to use the patch method. Okay, we typically like to use patch method to represent the main channel, especially for transport processes. But that's okay. You can just use the paving methods. Okay, to show you an example of the patch here, you can see that we represent the main channels using patches. If you look at the mesh type, that's a patch. So a patch inside SMS requires exactly 4 vertices. Okay, so this is important when you create a new patch. You must review all the neighboring patches because SMS does not automatically check this for you. So this is one of the main source of frustration when using SMS, is that when you try to generate a grid from all those polygons and they are halfway or towards the end, it complains that some polygons are ill-formed. So if you really get stuck, what I suggest you do is use divide and conquer. Basically, you select all the polygons in the south delta, for example, and try to match them. If it goes through, that means the problematic polygon is not here. Then you go to the north delta until you zoom in and find the problematic polygon. Okay, let's look at a specific run. This is a San Francisco Bay and Delta run, and as you can see, I've created all the inputs. Okay, so there are several types of inputs needed by SELFE.gr3 file, which is grid-based inputs, and .th file, that's time history, and atmospheric flux file as flux directory, and .ic file, that's initial condition. .in file, the in file, consists of a major parameter, vertical grid, and boundary conditions. Okay, so let's go through those input files category by category. First of all, .gr3 file. As you can see, most of those files are symbolic links. I like to use symbolic links, especially when you have many runs. You can see that most of those gr3 file symbolically link to previous runs. Okay, the only thing new for this run is the rough.gr3, which specifies the bottom roughness. So there are many advantages of using symbolic link, including save the disk space, also provide better provenance. But there are things you need to be aware of when you use symbolic link. For example, you cannot use too many layers of symbolic links. You eventually break them, so you may want to periodically redefine your link to older run. Another thing of symbolic link is that when you try to edit a particular linked file, you are essentially editing its source file. Okay, it points to. So this may be a very bad practice. So if you have to edit a symbolic link, you should remove the link first and physically copy that file to this directory before you make any changes. Another thing is that once a run is completed, it's always a bad idea to change the to edit the input files, because there may be symbolic links that depend on this particular file. So if you want to make changes to a completed run, I suggest you make a new run. Okay, so the easiest way to visualize and edit and prepare those .gr3 files is using the ACE tool. So ACE tool can be downloaded from the SELFE website, and because ACE tool was initially developed specifically for LCirc and SELFE, so you can get a lot of free mileage out of them. So I strongly suggest you spend some time and install ACE tool and your local system. You have much easier life. And our experience is that most of the standard installation of Linux will already have all the graphic packages needed by the ACE tool. So you shouldn't have too much trouble installing ACE tool. There are three major tools under ACE: XMGR Edit for grid editing and visualization, XMVs for visualizing the SELFE outputs, the binary outputs, XMGR5, which is a lightweight 2D plots. Okay, so now let's fire up XMGR Edit .gr3. So this is how the grid looks like. Shrink a little bit. So the very first thing after launching the GR-Edit I usually do is to go compute the boundary. The reason is that when you zoom in and zoom out, you don't want to see all those elements being redrawn. Okay, so now you can turn off the grid elements. You only show the outline of the grid. Okay, now you can zoom in and zoom out quickly. Okay, on the left, you can see some commonly used tools under GREdit. For example, you can zoom in specific area, and you can auto scale and zoom out, zoom in is zoom out and translate. Okay, and using GREdit, you can load up to 2 grids. First is called the foreground grid or edit grid. That's a grid you can make modifications to. And the second grid is called background grid. That's usually reserved for DEM grid. You cannot edit this grid. Okay, but you can use the background grid information to know the depth from background grid to the foreground grid. Okay, now let's load the delta DEM grid. So read data and toggle this background grid and go to the directory DEM old. So this is this delta DEM grid. Click OK. You will load the background grid for you. It take a while because it's a large grid. Okay, now you say cancel. Okay, and if you want to take a look at the background grid, you can depress this button. It will show you the background grid, and by default the background grid color is in orange, whereas foreground grid are in black. Okay, so this is how the background grid looks like now. To save time, we compress this button. Okay. Now you can load the bathymetry information from the background grid to the foreground grid. You go to grid DEM. First one, load bathymetry, and you have 2 options here. Okay, and then you click accept. You load the bathymetry information from background grid to foreground grid in the region covered by the background grid. Okay, well, I can do that here. Of course, you can also visualize the bathymetry of the foreground grid and background grid using these 2 buttons. Okay, but first of all, you need to define the legend. So you go to display isolines of foreground grid here. Okay, let's shrink this a little bit. Okay. Okay, so specify the starting value, so 0, and step 2 meters, and then accept. You can see all those values are now updated, and you can change the specific value by toggling this button, and then, for example, last one you want to change it to 100 meters. Accept, and then you can put the legend anywhere you want in the grid. Accept. Done. Now depress this button, isoline. You show the bathymetry of the foreground. Okay, now you can see the first 2 colors are very close to the white. So to make them more distinct, you can edit individual colors by going to display colors. Okay, and you can see 3 rows of colors. First one is for the annotation. They are reserved for the foreground grid color, background grid color, etc. And the second row is what we need, the bathymetry. Okay, the first 2 colors are too close to white, so we want to change them using the RGB dial. Okay, now they are more distinct. Done. Redraw. You should be able to see better color. Okay, now to save time, we unclick this. You can go to specific element, node, or XY location by using this locate go to. Okay, so for example, you want to go to load 101. You click, the cursor will point to the load 1.1. etc. And similarly, locate, go to XY. You just specify XY value. Okay, next I'd like to show you how to visualize the serial number inside XMGR edit 5. As I said before, serial number ideally should not fall below 0.5. So to visualize that, you go to Special, Dimension is Numbers, and under Courant number, you type in the time step you want to use. For this step is 120 seconds, and the warning value is set at 0.8 by default, and the unacceptable value is 1. So those two, the warning value and the unacceptable values, are terminologies for the explicit model. That's something you need to remember. Okay, so for implicit model like SELFE, it's just opposite. So 1 and above will be good. So to see the Courant number in contours, press this display field, accept. You see lots of red coming out, which means good. Red means serial number is 1 and above, and orange means it's between 0.8 and 1. Green means it's below 0.8. You do see some green here. That's because the depth here is 0 or negative. So serial number is not defined, so that's okay. And you can also look at the Courant numbers, the specific numbers, and each grid node. This will take a while to load, but basically you'll show all the Courant numbers and each grid node. Okay, turn this off. Next, I'd like to show you one very useful way to generate .gr3 file and .ic file. For example, if you want to generate the salinity initial condition file that varies from 33 PSU to 0 in this small region, you can simply go to Edit, Edit over Grid Regions, and Evaluate. Click that, and make sure toggle is on entire grid, because you want to initialize the depth to be 33 PSU throughout the grid first. Accept, and then you create a region. Go to region and create a region here, and you can see the cursor becomes cross like here. So you create a polygon by clicking all its vertices. Okay, here. Now you zoom in. You want to evaluate depth inside this region, so you need to find the x minimum and x maximum. You're just going to copy down here. Okay, now you go back here and define the region, make a linear function in this region. Okay, and additionally you want to impose the minimum and maximum value. Okay, so you don't want to get negative salinity. Accept. Now you can make sure that what you've done is correct by looking at the contours. Okay, go again, because you are working on the edit grade, you want to look at the isolines of bathymetry for the edit grade. So now you can see the limits have been updated. It's between 0.27 and 33 PSU. So you go here, auto scale. You automatically update the start step for you. Accept, done, and turn on the control line. You see the linear transition in this region. You are not done yet. You need to set the salinity in this upstream region to be 0. So you create another region, clear the existing region, and then create another region here. And when you are about to close the polygon, you just press the middle button. Okay. Now you want to set the depth to be 0 in this region. Okay. Now you can see that this region, the depth is now 0. If you go to locate, find nearest node, you can click around in this region, and you can see it's a node number, x, y, and depth equals 0 now. Okay. And lastly, you want to save this as sort.ic file. Make sure the toggle is on edit grid. You want to save the edit grid, not others. So accept, done. That's it. Okay, next let me show you how to generate open and land boundary condition segments inside XMGR Edit. Before you start, it's always a good idea to have a very good idea on the spatial distribution of those segments, because you want to go through those segments in a fixed direction. I usually follow counterclockwise direction for the exterior boundary and clockwise direction for the interior boundaries. Okay, before you do that, because you want to zoom in and zoom out very quickly to find some very small open boundary segments, so you want to go reset the default scroll percentage and expand the shrink ratio here. So the original is somewhere here. Now I already increased to 35% and 159%. Okay, you want to make sure that accept. Now you should be able to zoom in and zoom out very fast. Okay. Then you go to Grid DEM, create open land boundaries, and first one, define open boundary segments. You always define all the open boundary segments first before you do all the land boundary segments. Okay. So there are 3 open boundary segments for this grid: 1 ocean and 12 rivers. So we go in counterclockwise direction like this. This is last open boundary here. Okay, so first of all, the ocean open boundary starts from point this here and ends here. So you just click beginning point and click again and unload. You can see this segment now becomes blue. So in order to confirm, you need to press the middle button. Okay. Now you refresh. You can see that this color is changed. Now let's go to Coyote Creek. Do the same thing, beginning and confirm. The third one is Rock Creek through. It's here. Okay, again, counterclockwise direction. It's always a good idea to follow this convention. Okay, and the next one will be somewhere along the old river channel. So you can use this locate, go to XY, and this is you input the XY coordinates of this boundary load. So I already put it here. You go accept, you point to that particular point. Okay, you zoom in around there, and you can also pin it down here. Just put a fixed point and accept with the middle button. You can see now this small circle means it has been marked. So you want to turn on the grid around here, and we know that this open boundary consists of only one element y. Okay, so go back here, define open boundary segment, beginning and confirm. Okay, turn this off as we want to zoom out. So this is the next open boundary is here. Okay, do the same thing. Next one is the CWP. Next one is San Joaquin River. This one is Canavary. Somewhere here. Yep. This one is North Delta. And Sacramento River. And Yolo. So this way you can go in and out very quickly. And North Bay. last one is the Nampa River. Okay, we have done all the open boundary segment. Next is to fill in the land boundary segment in between. Okay, you click define new land boundary segment here. Again, do very similar thing. You start to click the pin node point and link to the ocean boundary here. Okay, confirm with middle button. Next one, ocean. Now you can zoom in and zoom out very quickly to Coyote. So I just made a mistake here. Should I use land boundary segments? Okay, so unfortunately, well, let's try this way. Okay, now define new land boundary here, and then here. Okay, now it becomes a land boundary, and then from Coyote to Rock Creek, make sure it's a land boundary. Here. Okay. Next one is Old River. You can see there are fixed point here, circle, small circle here. Zoom in there. Zoom in a little bit further. Okay, now you can see the two end nodes. This is SWP. Here, and CWP, and then San Joaquin River. Okay, Calvary. Here. And here. Sacramento River. And then Yolo bypass here. Zoom in. North Bay. And then lastly, go back to Nampa River. Now that concludes the loop around the exterior boundary. Now if you auto scale, you can see that the boundary has been assigned. Okay, again, this boundary, we made a mistake. I should have used the new land boundary segments. Instead I used open boundary, but we can fix that. If you make a mistake, you have to clear all. Okay, you'll go back to red colors. Now you can see that the exterior boundaries consist of open and land boundaries. Okay, so it's maybe not easy to see, but you can see this is an open boundary and it's a land boundary. And another thing you notice is that the interior boundaries, the islands, are still in red. So you don't have to do anything if there are no open boundary segments on those islands. Okay, so they will be kept at internal island boundary. So if when you satisfy with your selection, you save it, the open boundary, land boundary segment information to the file. Okay, done. Okay, now you go back to the directory e.temp. You can see that we have 14 open boundary. We should have 13 because I made a mistake there. But this part you just append to the end of hgrid.gr3 to complete that file. Okay, we have done that already here. So all the open boundaries is the correct information we generated before. Okay, so once the open boundary and NAND boundary segment have been generated, I highly recommend you to do a pre-processing run with SELFE. Okay, just in case there are illegal elements like overlapping elements, etc. So you'll be a waste of your time to complete preparation for other input files. Then later on you found that your grade is not legally formed. So to do that, just go to param.im and turn this pre-processing flag on. Okay, before you can run SELFE, this is the compiled code here. You need to make a directory called outputs. Okay, that's where the outputs go. And then you just run SELFE with only one CPU. Okay, with more than one CPU, the SELFE will complain to you that the pre-processing can only be done with one CPU. Launch it. If it's successful, then you'll get a message saying pre-processing successful. If not, then you need to look at a particular error message file. I'm going to show you. Okay, now you can see that our grade is good, but if not, then you need to look at output rogue. Now you don't see that file because our grade is good, but it's called a rogue something. Okay, and that file, particular file, will show you all the violating sites. Okay, with the load numbers for its two end loads, so you can zoom in quickly, look at the problems. Sometimes the fatal error information is inside 4.11 as well, so you should check that. Now this is very important, especially when you use this interval parameter equals 0. Okay, if it's equals 0, then the grade, the code will check for Shapiro filter violation. So if you have those kind of violations, the preprocessor will tell you where to fix those boundary sites and elements. Okay. Now we are using 1, so the model can accept any generic unstructured grid. So now let's just put the preprocessor flag off. Let me show you some typical SELFE outputs. You can see mirror.out, that's the main message, output message, 4.11 fatal error message, 4.33 solver information, and inside outputs you have a slew of outputs including the domain decomposition information. And after pre-processing is done, you will see 2 build point files coming out. Okay, the build point format is very similar to .gr3, except at the end of it you don't have a collectivity table. Okay, so centers and site centers .bp, they are for the element centers and site centers. So you may want to triangulate both of those build point files to get centers .gr3 and site centers .gr3, which are needed if you want to visualize some non-standard SELFE outputs. So I'm going to show you how to triangulate with gredit. First we load the horizontal grid. Again, first thing, compute boundary, turn off the element. Now you read, make sure this points to build points, and you can filter the directory here. For example, you can load in the element center, say OK, cancel. You can see this style here. It controls you want to show all the build points, by default it's depressed, so you will show all the build points. If you refresh, you see all the element points. To triangulate, you go to build, triangulate. There are two triangulation methods: Fortune sweep line and Shusha triangle. I like to use Shusha triangle, and because we don't have any redundant points, just specify minimum depth distance of 0. You say apply, it will triangulate for you. This is a large grid. I'm not going to do this. It will take some time, but after that you just save it as centers.gr3. Again, make sure this points to a new edit grid. Okay, very briefly I'd like to show you how to visualize domain decomposition. So this is another one I have done. So we load the horizontal grid here. Okay, this is a bay only grid, and then for this run I use 48 CPUs to show the domain, how the domain decomposition is done. In this run, you go to Special, Properties, and see Read, and the partition information is inside the output directory. So select this global to local.prop file, and it's very important to select property and elements. This is because domain decomposition inside SELFE is done on an element basis. Okay, so the process number are defined at element centers. OK, cancel. Now you want to display the information as contours, so depress this and then define isolines. Make this smaller. Now you can see. You say auto scale. Now you can see that the on the top limits is between process 0 and 47, so 48 CPUs. You see auto scale, accept, done. Okay, now this is how the domain decomposition is done. If you want to query a process number for a particular location, you say query. So this particular place belongs to process 1. This particular is process 28. Again, you may want to make the color more distinct, because it looks like there are lots of white space, but they are actually not. So in order to do that, go to Display Colors. So again, second line, make them a little bit more distinct. Okay, now you can see all the domain decomposition colors. Okay, one more thing about the outputs. So many outputs inside the outputs directory are process specific. For example, the hard start output. Okay, you can see many files, and the first, the second number here represents the process number. So you usually need to combine those outputs to generate a new hard startup in order to use them. Now let's look at the main parameter input. I want to show you how to adjust some key parameters in the process of tuning the model. Okay, so the first parameter is a 2D and 3D model right here. Okay, so just want to remind you that the 2D models is a simplified version, therefore it does not have many modules available. For example, the transport model, you cannot be used with a 2D model. The second parameter is this transport. So suppose you are using the barotropic model and you want to save time, you may want to turn this off, so transport equations will not be solved. The next one is the hard start parameter. Okay, so you have a choice of 0 means cold start, 1 or 2 means hard start. Okay, so 2 is relatively simple. Basically, just imagine for some reason your run crashed. You want to restart from a certain hard start point. Then you just set I hard equals 2 and prepare hard start.in from that any specific step you want to hard start from. And in this case, you do not change any parameters. Okay, you may change the number of CPUs used, but you do not change any parameters, including the ramp-up flags. So in the case of hard start equals 1, it's similar. You also need a hard start.in, except that now you reset the model time t equals 0. Okay, so whatever time read in from hard start.in will be reset as time 0. So you are starting from the hard start.in condition. So in this case, you do need to change any time-dependent inputs like a .th file, sflux file, and if you are using the title boundary condition, you also need to update the node factor and equilibrium arguments. Next parameter is this interval parameter. Okay, so in general, you should always start from interval equals 1 because you can take any generic unstructured grid. And for some coastal applications, you may want to try interval equals 0, which has some nice properties. Okay, so that's something you may want to tune. But bear in mind that when you set interval equals 0, the requirement for the grid is higher, so you will check for Shapiro filter violation, so you may have to fix some boundary elements or even some skinny elements. Next parameter is the inundation flag. Okay, so you can choose 2 inundation schemes inside SELFE, 0 and 1. And 0 is default for tidal scale inundation, and the inund flag equals 1 is for smaller scale inundations. And if you set this flag to be 1, then you generally need to reduce your grid size and also need to reduce the time step. So this is something you need to be aware of. Next is the implicitness factor, theta I. Okay, so as indicated here, this value varies between 0.5 and 1. So you cannot use exactly 0.5 because it may cause the model to blow up. So if you really want to use a value close to 0.5, you may use 0.5001. So generally speaking, when you tune this parameter towards 0.5, you have less and less damping, but more and more numerical dispersion. So for example, you want to maintain the wave amplitude for a long time, so you may want to reduce this parameter towards 0.5. The most important parameter perhaps is the time step. Time step is very important in SELFE because of self-fill condition. So it's always a good idea to start with a large time step. And how large you want is really a problem specific, but for barotropic simulations, we found that 200 seconds or thereabout is about right. And for baroclinic, it should be slightly smaller. For example, this particular run for San Francisco Bay, it's a baroclinic run. We use a time step of 120 seconds. Okay. In any case, it's always a good idea to remember that to check the grid. So this time step, choice of this time step is closely related to grid generation. As I have shown you before, you should always check the self number to make sure that it's not excessively small. Next is the transport algorithm flag. I upwind T. Okay, so to really do a really good job for the transport, you need to pay attention to the grid. For example, resolve the channel faithfully as I indicated before, and preferably using punch methods. So of course I structure grid along for the channel, and you also need to use the second order upwind density TVD methods. Okay, but TVD method is explicit, so you need to be aware of the cost of using this particular algorithm, and there are some additional handles if you use TVD. For example, the cutoff depth HTVD. So you basically below this depth, the program will use the upwind, which is much more efficient. Okay, because the TVD is restricted by the Coulomb number, and Coulomb number in the shallow region may become large, and so you are forced to subcycle many times. So this parameter helps you relieve that bottleneck to some extent. And another parameter or input you can specify is the tvd.gr3. It's not shown here. This is not updated here, but it's this input. So this input controls in which region you want to use TVD and in which region you want to use upwind. So I do have some additional utility scripts to help you in the process of grid generation for TVD. So you're welcome to contact me to get additional guidance on how to use TVD efficiently. Okay, next parameter is this the atmospheric option flag. So just want to mention that if you set this parameter to be 2, and this next one, the time interval, you want to set this generally to be same as the model time step, so to make most out of the SFlux file. The turbulence closure flag. Okay, so in general, ITER equals 4, that means Garten. You have to compile with a Garten module. Gives you better results than ITER equals 3 if it works. The only problem with ITER equals 4 is that it's sometimes it gives only n, but if it works, generally it gives you better results. And for the output, okay, here, this particular integer, you want to make sure that your total runtime is evenly divided into stacks. For example, you have a 21 day run, and you want to set this particular integer to be correspond to say 3 days or 7 days. Okay, but you don't want to set it to be 5 days. Otherwise, the last stack will be an incomplete stack, and that will cause some problem for some post-processing scripts like this. Another thing is that the hard start output file interval. This one must be multiple of the previous integer. And if you want to use this to visualize the vertical profile, it's always good to turn on this output Z-core, which gives you Z coordinates. Okay, so now you have prepared all the inputs. You just launch the run, and when the run is still ongoing, you may use this Perl script to automatically harvest all the binary files to gather them into big stacks. Okay, so this is really a robust and a simple Perl script I wrote. So just a few things to be aware of. Number one, you first need to compile this Fortran code called combine output 6.f90 and make sure that the path here is correct. Number 2, you want to make sure that in your run the elif.61 is part of the output, otherwise this proscript will hang. Another thing is that as I said before, you want to divide the total runtime into even stacks. So this ensures that the last stack plus 1 underscore will be output. So for example, if you have 3 stacks in your output, the 4 underscore should be output by the code if you choose the IHF skip parameter properly. This is important because this proscript will always wait for the next stack to come out before it combines the previous stack to ensure that the combined outputs are complete. Okay, so there are many post-processing scripts we wrote. Here I like to just show you quickly how to extract time history, time series, and multiple points. Okay, so we already combined. Okay, so this particular one is 140 days and 10 stacks, so each stack is 14 days. So we want to, suppose we want to extract the time history of elevation, and it's 12 points. Okay, you can see this is a .pp file, build point file, and the 12 build points here. And you notice that I repeated each build point for x, y, but the z are different. This is useful if you want to extract 3D variables, for example. So for this particular case, this build point file can be used to extract the surface and their bottom salinity. But for elevations, the 2D variables, you get identical results for the surface and the bottom. Okay. Now, so this is the only input you need besides the binary output as elif.3, elif.61. So you just use this particular Fortran code, read output 7b group ZFS2, and answer some online questions here. The extraction points format, that's the station.bp, so we are using the build point format, so we use 1, and this particular one was done using Cartesian coordinates, so it's number 1 here, and you input elif.61 here, that's you want to extract elevation, starting stack 1, last stack 10, and this particular input Corey day, if you don't have any, just put 0. Okay, so you'll start from day 0. Okay, after this is done, you should say 4.18 and 20. 4.20 shows nothing but the bottom depth at each of the 12 build points. And the main output is 4.18. You can see the first column is the timing days, and followed by 12 elevation values. Okay, let me show you how to use XMVs to visualize the self-binary outputs. This is the most fun part. So you inside the XM output directory, you launch XMVs. Any of the binary output, because only the header has a grid information. So the window should look like this. You see the outline, the boundary of the grid. Okay, so as you noticed, on the left hand, the toolbar looks very much like XMGR edit. Okay, The only difference is now you can load up to 5 grids. 1, 2, 3, 4, 5. Okay, so the way to load a different grid is to go to Files, Grids, load as number 2, and select a grid. Say OK, cancel. That's it. Okay. And another thing you notice is that you can of course visualize the grid elements and the grid bathymetry. In order to load the visualize the grid bathymetry, go to View, Grids. Okay, it's a little bit smaller now. Okay, so this pop-up window and define isolines. Suppose 0, step 2, say OK, and you can display legend anywhere you want, accept, and you can see the first two colors are too close to white background color, so you can redefine the color just like GR edit, second line. You may change any color you wish, accept, done, accept, make sure this button is depressed, and you say draw. Okay, so this is how the grid bathymetry looks like. Let's turn this off for the time being. Okay, so with XMVs 6, you can visualize the binary output in 3 ways. This horizontal slant, the sample means the vertical profile at any given point, and the transects. The last one, the transects, requires a different methodology. I'm going to talk about that later. Okay, let's first look at the horizontal slabs. Okay, so this is how you launch the SELFE slabs, and the SELFE surface button is a special case of the horizontal slab. Okay, so let's try to load the first stack of elevation. So elevation is 2D variable, so it doesn't matter it's a surface or bottom, it's the same one underscore. And you can see in addition you can sample the time step here, depressing this, and you can sample it, and you can also append flow. That means you can press after you load the first stack, you can load the second stack and append to the end of the first stack. Okay, so accept. Okay, another window pops up. This control window allows you extra control for the display of vectors and scalars. So this is a vector section, this is scalar section, because elevation is a scalar. So you want to display using isolines. Define isolines. Give the starting value -2 meters. Step of say 0.3. Okay, and you can display legend anywhere you wish. Accept, done, accept. Now you can see the color coming out. So this is a surface elevation. Okay, and you can use the animation tool to animate it. Okay, and stop. And then on the upper right corner you can see the time in seconds and frame information. So we have read in altogether 336 frames. It's a fixed frame. So if you want to visualize the timestamp, you go to View, Time Info String, and depress this and pick a location. Accept, draw. Okay. So this is a date information, and this particular information we got from the first line of bctypes.in. Okay, if you follow this format strictly, this should be able to automatically show you determine the calendar date. Suppose that you are not interested in the calendar date, you're just interested in time, in day, hours, for example. So you go back here and then toggle it, day, hour, minute, minutes, and seconds. Accept, close, now show the timing from the start of the run. And by using this animation button, you go to all the end of the record. So you can see that the first stack has 14 days. Okay, and you can animate backwards if you wish. Okay, and one thing I like to mention is that this allows you to load in up to 5 flows, so-called flows. Okay, so you can load on top of the elevation, the velocity and the salinity. Okay, to do that, go to Files. Now suppose you want to load the salinity and 5 meter depth. You use SELFE and the input 1_salt.63. You press this with depth, and depth information is inside 1_z_63, and the input depth in meters, say 5 meters. Okay, that means z equals -5 meter. And in addition, you can sample it, subsample the time step. You can also append to active data set like before, except. Now you can see that this is asking you, do you want to overwrite the flow number 1, because flow number 1, remember, has been assigned to the elevation. So cancel. You want to load this as flow number 2, accept, then this will not complain anymore. Or if you wish, you can overwrite. There's nothing wrong with that. Okay, now finish loading. You can see that this number has been updated to flow number 2. Okay, because salinity is also scalar, so you want to display isolines and define isoline from 0 to 2.3, accept, and you can display its own legend here. Now, because we have 2 sets of scalars, you don't want the colors to interfere with each other, so you go back to flow number 1 and turn off the isolines. Okay, and go back to flow number 2, that's a salinity. Depress this, accept. This is a salinity and 5 meter depth, and of course you can animate it as different. Now on top of that, we want to load flow number 3. Okay, using the surface velocity. Okay, accept. Okay, now because velocity are vectors, so you need to display and loads. Just say accept. See vectors coming out. So in order to see the vector scale, go to View, Velocity Scale, and you can change the numbers if you wish. Depress this, display, and pick a place to display the legend. Accept, done. Now you see the velocity scale. Okay, so what you see now is the surface velocity overlaid on the salinity and 5 meter depth. So you can animate it, and if you want to, okay, pick a viewport, and then if you want to generate animation, okay, you can use this command, and another window pops up. Under command, you type bench run frame. You want to start from frame number 1, say, and frame number 20, and return. You generate a bunch of you go back to this directory, you see a bunch of GIF files. Okay, and each GIF file will look like, will correspond to one particular frame. Okay, and then you can use tools like GIF cycle to generate animated GIFs. Okay, let's go back here. Okay, next let me show you how to look at the vertical profiles inside the vis. First of all, we just clean up here so it don't look very busy. Okay. Now, to look at the vertical profiles at any given point, you use SELFE sample. Okay, another window comes up, and the data file, for example, you want to visualize the salinity profile, and the Z-core file, of course it is Z-core, and you want to pick any particular point. For example, we want to look at a point inside the Caquinas Street. Pick here, read data. After reading is done, you depress this to location marker, and it's very important to auto scale. So you can see x-axis is in seconds, so for 1 hour to the 14th day, and y is actually z. So this particular spot, the depth is about 30 meters. Now remember, you are visualizing the scalar, so you need to define the ISO lines. Here you auto scale and then display legend here, accept, done. And after all this are done, you want to place the profile windows here, accept, and when you go all the way to the end of the record, you can see the vertical profile of salinity. X-axis is time in seconds, y-axis is z. Okay, and of course you can increase number of ticks for the z-axis, for the y-axis, accept. Okay, and then again, you are allowed to load in up to 5, actually 10 vertical profiles. So as vertical profile number 2, we want to look at the velocity profile, and another point, any point here, this point, read data, and depress this to auto scale. Because velocities are vectors, you do not need to define the ISO lines. So you just place anywhere you want, accept. Now it's a little bit outside the domain, so accept, draw. Okay, so this shows the vertical profile velocity. So you can animate backwards, for example. Okay, and again, similarly, you can use command window to generate animated GIFs if you wish. Okay, now lastly, I'm going to show you how to visualize the vertical transects. Okay, in order to do that, we have to first generate a transect, the BP file, the build point file. So because XMVs does not have a BP, a build point format, so you need to go back to XMGR-edit. Here I already loaded this horizontal grid, GR-edit, and the bathymetry. So suppose we want to visualize the transect along the channel from here to here. So you go to build, place build points, starting from here, just click in order. Doesn't have to be equal distance. Okay. Click as many as you wish. Okay, after you're done with the last, use the middle button to confirm. Now if you refresh, you can see those build points generated. You need to save them as build points. Make sure this toggle to build points. Okay. Just save them as transect.bp. Accept. Done. Okay, now we go back to this. Because the vertical transics have very different spatial scales, horizontally and vertically, so you cannot use the previous vis window. Instead, you launch another vis and command graph type XY. Okay, because of the different scale. Now you should see nothing, no grid, nothing. Okay, and then you go to Files, Self, Sigma plus Z grid transects. The command window pops up. And suppose you want to look at the vertical transect of the salinity. Depth file is Z core, and this vertical velocity is also needed for the velocity transect. So we just put it there, and the BP file, the transect file is transect. BP we just generated, and you can subsample steps. Can you accept? Okay, maybe this. Let me see. Okay, it's in the same directory, so put a path 1. Okay, now accept. This window larger. Okay, so this pop-up window, so again you can load up to 5 transects. Okay, this transect number 1, salinity transect, along that transect we just designed. So we depress display transect. Always do that because salinity is scalar. You need to define isolines. Okay, auto scale, and you put legend anywhere you wish. Accept, done, accept, and now it's very important to auto scale. Okay, so this is a salinity transect. So put the legend horizontal so it does not block any view. Okay. Now, if you move the cursor around, you can see on the lower right corner that's the XY, so Y is actually Z. Okay, and if you wish, you can also visualize how the transect grid looks like. Accept. Okay, and the leftmost place is correspond to the first build point, and last one is the last build point. Okay, and of course you can animate them. Okay, and you can now load the velocity transect and transect number 2. Accept. Okay, now you need to go to transect number 2 and display transect and vector horizontal. Okay, because it's vector, now you don't need to define the isolines, just accept, accept. Now you see all the horizontal vectors. Again, you can use the command window bench run to generate the animated GIFs. Right now, this transect does not allow appending function. There's a bug inside it. So if you want to generate a long animation, so you can use this command window, load each batch, each stack, and use command window to generate GIF files and concatenate them using GIF-SQL. Okay, lastly, I want to show you how to look at the time histories of anything at any particular point inside this. For this, we return to the SLAMP section. As you recall, we have loaded 3 flow fields. Number 1 is the elevation, number 2 is salinity and 5-meter depth, and number 3 is the surface velocity. So in order to look at the time history of those variables, you go to Models, Time Histories, and the window pops up. You depress the first 2, and it's very important to auto scale here. So x-axis is time in seconds. Okay, and then you go to Display, Now you can see that the last two rows are what we did. Okay, so the elevation really means any scalar variable, whereas velocity means any vector variable. Okay, so if you remember, the first flow field is the elevation, second is salinity, third is the velocity. So suppose you want to visualize the elevation at any particular point, you just depress this and make sure this color dial is anything but the white. Okay, accept, done, and then you place anywhere you want, this place, and then click again, accept. Okay, now this particular version of this I'm using as a box, so by right you should see time history window here, but in any case you can use this view button to look at the time history. By pressing this view button, you will launch XMGR5. Okay, so this is the elevation time history. Okay, and now suppose you want to look at the time history of salinity. So number 2, accept, done, make sure elevation, make sure, as you can see, you can load up to 10 history markers, so make sure other history markers are clean. So one here, accept, okay, go back, and the salinity is selected, place, say salinity here, accept, view, you see the salinity time history and then particular point. And lastly, you want to visualize the velocity magnitude. So velocity is in field number 3. So depress that, make sure color is anything but white, accept, done, place, here, click again, accept, view. So this is the time history of the velocity at this particular point.